and welcome to this webinar on electric vehicle battery immersion cooling, organized by Carrar, who gently invited me to co-present this webinar. Hi, I'm Dr. Cecile Pera. I'm an expert consultant in automotive technologies. Many of you know me for what I share on LinkedIn. If you do not know me, please consult my profile on LinkedIn later after this presentation. I'm here today to present with Eitam from Carrar. Hi, Eitam. Can you present yourself?
Hello. Yeah, thank you, Cecile. Hi, so my name is Eitam Friedman. I am the VPA of R&D. Thank you for joining us today.
Okay. So let's start. I guess people have arrived. So how is that organized today? We are here together for about 1 hour webinar. We are going to talk, Eitam and myself, for about 40 minutes, leaving us about 20 minutes for a Q&A session at the end of this webinar. So please type any of your comment or any of your question in the comment in the chat box of Zoom, and Tal from Carrar will gather this question to ask the question to us at the end of this webinar. Meanwhile, we have different sections. So first, I will start to talk about how far we are from seeing battery immersion cooling introduced in on-road cars and vehicles. Then I will talk about the difficulty for thermal management and see the different philosophies that exist for thermal management and why immersion cooling is interesting and why so people are so interested in immersion cooling. Then Eitam will detail what is two-phase flow. Sorry, I need to learn. We don't say two-phase flow. We must say pool boiling because there is a difference. And if you don't know the difference, please stay because Eitam will explain you about that later in the presentation. Then we will have some question and answer about the usual concerns that people have on immersion cooling. And they are questions I have been asked many times during discussion I had with many people. And then Eitam will present a lot of results obtained by Carrar on their technology on this immersion cooling. And then, of course, the Q&A session. So let's start. So I like to start with the why. And very often, as a consultant in automotive, I, of course, talk a lot about thermal management for battery for electric vehicle. And very often, people ask me, okay, Cecile, but how far are we from seeing this battery immersion cooling? Is that going to really happen in commercial cars, in commercial vehicles? First, you have to know that there already exist examples of battery immersion cooling. Probably you know that in many performance and racing cars, high performance batteries are already using immersion cooling. This is the case for things like hybrid, for Formula 1, for example, but also for full electric vehicle, for Formula E. I put here on the top left corner an example of a FIA racing series called ETCR, and that is using battery immersion cooling. But okay, you are going to tell me that here we are talking not really about cars that are on the road. We are talking about example for racing application, and it is nothing like a car you can purchase normally. On the road, if you're lucky, you can see already cars that are using immersion cooling. I put here two examples. So the one on the left, the red one, is a Koenigsegg Regera. This is a hybrid hypercar using immersion cooling. The battery pack has been developed by Rimac, but it's one of the first battery immersion cooling that I know that have been used on road. Another example is on the McLaren Speedtail, again, another hypercar hybrid. But again, you are going to tell me, okay, Cecile, those are cars that have been produced like 10 of them, maybe 100 maximum, but they are not cars for large production. They are cars that are now starting to be introduced. Among other examples, this is a battery pack developed by Mercedes. So the one in the middle you can see behind me. This is, again, a hybrid battery pack used in Mercedes AMG. You can see here they apply immersion cooling on cylindrical cells. I have reviewed this battery pack quite a lot, and it's one of the first battery pack using immersion cooling, I'm going to say, for slightly larger production. We are talking here about several thousand of cars that are sold. And another example, I took a picture myself, is from CES Las Vegas this year. This is an example for off-road. This is a digging vehicle for urban environment, fully electric, developed by John Deere and presented at CES Las Vegas this year. So they are using another type of immersion cooling. On top, you can see a picture of the full battery pack and a picture of the module here using immersion cooling. So again, what I want to say here in my introduction is that immersion cooling is not a far future. This is already happening. Those are examples you can see today on the road or on shows, and there are much, much more coming. Of course, I cannot disclose everything because a lot of the things I know are under NDA, but there are many, many battery packs using immersion cooling that are going to come in the next months and years. Things for motorsport application. So this is again another example of a motor sport, I'm going to say series, I don't know, but developed by Porsche. So that was 3 weeks ago in Hockenheim. This is, it's not an internal combustion engine. This is a full electric car. This is GT4 e-Performance developed by Porsche using a battery pack split in several pieces, but using again immersion cooling. And among the things I can talk, there are also battery pack of the coming Porsche Mission X, which is announced to be battery immersion cooling. Again, another hypercar, but there are many, many other cars coming. I know one car, mid-size production, I'm going to say we are talking here about several thousand of pieces per year with immersion cooling. And here I put another example on the right bottom corner. You have an example for immersion cooling under development for electric motorbike. So keep in mind, we are not talking only about cars and trucks and bus and things like that. We are talking about any kind of application for electric vehicle, so including motorbike, and also about mining application. There are also a lot of things happening for trucks, for mining, because they are requiring to get extreme condition for working, and immersion cooling is very interesting. So all of this to tell you that during the last year, everywhere I have been, would it be in USA, in Italy, in France, in Germany, everywhere, very, very often I talk about immersion cooling as one of the very hot topics at the moment in battery technologies. Why is this? Why is the automotive interested so much in immersion cooling? For different reasons. The first one, which is, in my opinion, the most important one, is safety. You know that battery fire have been bad press, and the industry is concerned by reducing the risk to experience battery fire. If you have a runaway, you want to stop the propagation before it's uncontrollable. And immersion cooling gets this potential to highly reduce the risk of thermal propagation and full battery pack fire. So this is an enabler for better safety for electric vehicles. Second, we have already talked about that, performance. I'm not going to detail that, but you understand. And the two other points are fast charging, because immersion cooling, by enabling better control of the temperature, and we are going to see that with Eitam, enables the fact that you can fast charge better, so you can achieve fast charging. And because you have an absolute control of the temperature spread in your battery pack and on your cell, this is also a good enabler to extend your lifetime. Again, we will see some data presented later with Eitam. So we say that thermal management is super key. I guess if you are attending this webinar, you are well aware that batteries need to be kept around a very narrow range of temperature. And why thermal management is that so difficult? We are cooling internal combustion engines since years and years without difficulty. Why is that more difficult for batteries? It is the fact that first, this temperature you are trying to keep is relatively close to the ambient temperature. Today, I'm in England, it is already more than 25 degrees Celsius. And if I want to cool down batteries that could be 30 or 40 degrees, it can be difficult because my big pool of temperature, my big amount of temperature in the air is already more than 25. So you need to trick the thermal management in order to be able to sink as much temperature as possible, even if this range of temperature is relatively limited. And there are many tricks we can apply. some for cooling plates, some for immersion cooling, but immersion cooling, especially with change of phase or two-phase flow, is a very good candidate for very efficient thermal management. The second problem of thermal management of batteries is not only the fact that you try to retrieve this heat, but you need to absolutely control temperature spreading over the battery pack and over the cell. Ideally, OEM would like to get 100 degrees maximum differences over a battery pack or over the cell. Why? Because if they can keep a perfect control over the temperature, they can know exactly how to manage them, so they age all at the same time, so you can extend the lifetime of your battery pack. And this is why so many people spend so much time on thermal management and why it's so difficult, and we are going to see what can make the thing specific with Carrar. So talking about thermal management philosophy, there are different ways, there are many ways to do thermal management. You know, you can do air cooling, cooling plate, or immersion cooling, but globally speaking, you have, I'm going to say, two kinds of person that they think about the thermal management. Because you have this difficulty to retrieve as much heat as possible, some people really want to increase the surface contact between the cells you are trying to cool down and your thermal management. So here my slide use an example with a cylindrical cell, but what I'm going to explain here is universal. It can be applied to pouch cell or prismatic. I just use a cylindrical just because it's smaller on my slide. But one possible philosophy is to say, I want to maximize the surface of exchange. So if I am on a cylindrical cell, or if I am on a pouch or prismatic, I want to get the maximum surface. So I want to stick my cooling plate or everything exchanging with this maximum of surface. On a cylindrical cell, for example, this is the kind of idea you have when you are running serpentine in between the cell, which have been popularized by Tesla, but it's used quite a lot now by many people. Another philosophy is say, I don't really care about this maximum of surface, I care about the preferential path to which the heat is going to follow. And this is something I have seen very nicely explained by people working at Rimac, for example. And in this case, you say, I don't really care about this transversal heat transfer. I care about the bus bar, I care about the tab, I care about the foil, and I follow this path. And a lot of people following this philosophy will use a preferentially cooling plates, could be underneath, could be on the bottom, could be in sandwiches, but they use this preferential path. Cooling plates can be different shape, can be different material, can be combined with thermal interface material for gap filler and things like that, but this is the global philosophy. In some sense, if we apply this to immersion cooling, we can say we have the both worlds at the same time, because we are able to englobe everything, so we can maximize at the same time the surface of exchange, also get the preferential heat transfer, and in this sense, immersion cooling makes the best of all the world because it gives a very efficient thermal management. But when you think about that, you need to keep in mind that it can have a cost in terms of the energy you are going to spend to do that. This is why it's so difficult to develop immersion cooling. In immersion cooling, it's a big family. There are many, many different ways to do immersion cooling. I have worked with different people on immersion cooling. And at Carrar, they have a very specific way to do that, which I really need Eitam to really explain that in detail. If you can explain that, Eitam, thanks.
Hi, thank you, Cecile. So if you have any questions, please write them on the Q&A and we'll be more than happy to answer them in the end. So to implement two-phase boiling, we have two ways or two common ways to implement boiling, two-phase cooling. The first one is two-phase flow, which is the most common the common method to use for cooling batteries, electronics. We see wide range of solution around it, from data centers to battery use case. And they use it because it's very hard to create good nucleation boiling, and therefore they're using specific heat and both latent heat. And most of the evaporation is occurring around the tabs and not on the cell surface, because there we have the higher heat flux as they are the best conductors. We at Carrar, we developed a different approach that also been tried and tested by other companies, as we'll discuss in the next slides how we solved it. but we went on pool boiling, meaning that the cells are fully submerged in the refrigerant, and we use the full properties of latent heat in order to have high heat transfer coefficient. So we have a liquid coming in and vapor coming out, and the heat transfer phenomena is because of the phase change. So every energy that's coming out from the cell is going to phase change, and it's not heating up the liquid like in single phase solution or two-phase immersion solution when you see liquid coming in and hotter liquid coming out, regardless if it's only single phase or any saturated liquid with some vapor in it. Okay, so the process of boiling is starting from natural convection. Okay, so this one on the right side is a graph of water, but just to explain how the phenomena is working. So when we start boiling, we can see and think about it like we're boiling water in a kettle or in a pot at home. We see first natural convection. This is the part when we see the water is moving a bit and the heat is going up, until we're getting to a point where we see some small bubbles going in, but they are collapsing inside the liquid or refrigerant, and this is the phase between point A and point B, again on the right side, on the graph on the right side. Here we have higher heat transfer coefficient because we can handle higher heat fluxes. But in the cooling and also in battery use case, we want to be somewhere between the B and C. There we have already bubbles that are coming up to the surface, and then we are taking the full advantage of latent heat, and we can apply a full two-phase, full pool boiling solution to the batteries. What is the challenge here? There was a challenge, and this is why a lot of companies tried. And then I'm going to the graph here on the left. This is a graph that NREL has performed a test together with General Electric. NREL is the National Renewable Energy Laboratory based in the US. And they try to manage this, the phenomenon of boiling incipients superheat, which means the delta T between the wall of the battery to the boiling point of the liquid. And the test was, the baseline of the test is the black line. And you can see that when the graph is coming back to the left, this is the point where boiling has started, and it's temperature difference of 15 degrees. And the heat flux that the first nucleation was generated was around the 1 watt per square centimeter. Why it's important? It's important because of two factors. The first one, the battery heat flux is very, very low. It's around the 0.1 watt per square centimeter. And when we want to implement two-phase technologies, we want to have a narrow range of temperature differences and not a higher range. And because of the pressure that we are working it, whether it is vacuum or high pressure. So they try to reduce the boiling incipients. So they did a nanostructure coating on, it was on a copper plate, and they managed to reduce this boiling incipients to 8 degrees. So let's say that the boiling point that we want the battery is at 25 degrees. So we need the boiling point now at 17 degrees. So if we have a refrigerant that boils at 25, we need to do a vacuum to 17 degrees. And then before the condenser, we need to increase back the pressure in order to condense it. At Carrar, we came up with different approach. We developed a solution that based on a mechanical structure, and we managed to reduce this boiling incipients to 2 degrees, meaning that we need only temperature difference of 2 degrees between the wall and the boiling point. And we also managed to have nucleation boiling at 0.05 watt per square centimeter. This is already the normal operation, more normal drive cycle of the vehicle. So we take full advantage of latent heat or also in normal conditions of the vehicle. So we get very good temperature uniformity on the cells.
So we can see here that we have explained with the introduction and what we explained here that we can have a very efficient way to make immersion cooling. But what I explained in the introduction is that in some sense, the difficulty is not only to make this efficient immersion cooling, but to make it efficient in the way you are going to pay. Why I'm saying this? Because it's still possible to retrieve more energy, more heat from the cell, but this energy you are running to cool down the battery is never coming for free. because in any system for cooling plate and coolant you are running in this cooling plate and so on, you need to run a pump, you need to run compressor, maybe you need to run chiller, many things. And all these things are not running for free, right? They need electricity, and guess what? This electricity is coming from the battery. So in some sense, it's paradoxal, but it's like that. The energy you are paying to cool down the battery comes from the battery itself. And if you are developing a cooling system very efficient, but you pay a lot of energy instead of running your battery and making a mileage, just cooling your battery, it's not very efficient from a commercial point of view in the electric vehicle. So this is what I'm calling the cost of cooling. What question I have for you is, Eitam, how efficient is this system? Do you need to get a lot of pump running, a lot of energy? How can you make something efficient in terms of cost? I'm not talking, of course, about money, but energy.
So it's a very good question, and everybody is concerned about this topic. So Carrar system, as we mentioned, rely on latent heat and not specific heat. Therefore, we don't need to circulate a lot of refrigerant to concentrate the temperature difference between the inlet and the outlet and the battery's use case. And because we're using pool boiling and all of the energy from the cell, all of the heat energy from the cell is going to the phase change, we actually need to circulate very low amount of refrigerant, so the flow rate is actually very low. If we'll compare it just as a rule of thumb, if other solution will need around the 10 liters per minute, we will require only 1 liter per minute, and we will be able to dissipate more heat. So the pumps are actually smaller, the power consumption is therefore lower, and we lower the parasitic energy that needed to cool down the batteries, also at high ambient temperatures.
So it's quite economic in terms of cost of running other elements, if I correctly understand, right?
Yes, you are correct.
We have also talked about the fact that you need to get uniformity of this temperature and remove as much heat as possible. So you don't want to get this homogeneity. Do you have an example or order of magnitude of how much heat you can retrieve to the maximum and how that works in terms of value?
So yeah, so this picture is what we are usual to see. We used to see temperature differences both on the cells and temperature differences between the different modules because of the flow, and regardless and how we will manage to design the cold plate, it will be very hard to manage the different temperature between the inlet and the outlet. And with Carrar solution with the same form factor, if you will compare a radiator to a condenser, we can dissipate around 25 kilowatts of heat from a normal size radiator, which is implemented inside the normal passengers' vehicles. And as we discussed in the previous slide, our system comes with a higher efficiency. So if we compare an apple to apple, and we want to dissipate 6 to 10 kilowatts like today's system are dissipating, we will having almost a passive system. So in terms of energy, it's much more efficient. And also we did the test when we wanted to keep the batteries at 25 degrees. So we won't see temperature increase regardless to the C rate. So 25 kilowatts of heat only from the battery packs correlates to very high C rates above 3, 4, or 5 C, meaning that we are now enabling ultra-fast charging.
Okay. I just want to mention that I have seen myself this target of 25 degrees when I visited you in Israel. It was super hot outside. And yes, I can see it was keeping 25, really 25, no more difference. That was quite impressive to see when I visited you.
Thank you.
Another question I have very often is about how heavy is that? Because space is one of the problems when you develop electric vehicle, but also weight. I personally think we will have limitation in terms of weight in future regulation coming. How heavy is that to run such a system? You already mentioned there are fewer components, but is that heavy?
So no, actually we showed that it's lighter. Because we don't need all the thermal interface materials and the aluminum enclosures, and etc., we actually managed to reduce the weight of the pack, or the mass of the pack to be accurate. And we already showed that on a 100 kilowatt hour pack, we can more or less reduce the pack weight by 20 kilograms. And this is due to the fact that we don't need a lot of refrigerant inside the battery modules. So on a typical 100 kilowatt hour pack, we will need approximately around the 20 liters of refrigerant inside. And in each and every module, there is a very small volume of refrigerant, because we're using the phenomena, as we spoke of, latent heat. And if we will compare ourselves to other components in the system, so in order to transfer the heat from the cell to the media in cold plate solution, we will have thermal interface material, aluminum enclosure, and other interface materials. Until we will reach the coolant itself, we will have a lot of thermal resistance along the way. And with our solution, we're taking the heat also directly from the cells, and we don't need all of these components. So we managed to save both weight and to reduce the number of assembly steps that are needed in order to assemble this the vehicle, the EV vehicle.
One question I have also really often coming now, so safety is one concern, but you can really hear people talking about sustainability all the time. So what about sustainability here?
So sustainability is highly important to Carrar, and because we demonstrated and we are still continue our testing, and we push the cells to the limit, and we also show that we can extend the battery lifetime over 3 times, and now we are almost passing the 4 times, but let's talk about the 3 times. We know that the pollution, the most polluted process in the EV world is the battery manufacturing process. And if we'll compare ourselves to ICE engines manufacturing to EV manufacturing, the ICE, the internal combustion engines, are actually less polluting than electric vehicles, and this is due to the batteries manufacturing. After some time, we get to the equivalent or balancing level after a few years that the EV is more greener than the ICE vehicles. And if we will want to increase or extend the vehicle lifetime from today's 8 to, I would say, 12, then a solution like Carrar is needed. And then we need to manufacture less batteries, and also after 12 years of working time, we will still be able to sell it to aftermarket like energy storage solutions. So we on the pollution level and GHG, greenhouse gases, and CO2 pollution, we will save tons of CO2 and greenhouse gases.
I want to mention for people listening that about lifetime, today the standard is, let's say, 8 years. Some people are talking about 10 years for warranty of batteries. But be aware that there are a lot of group of development. I'm going to call that, yeah, maybe some kind of lobby, trying to push over more than 10 years. I have heard people trying to push for 12 years, and I have also heard people trying to push for 15 years. Whatever the warranty for the OEM, we also have to think about second hands, because cars are here, and I have personally an old Jaguar, 40 years old, so cars can last very long. But just to mention that lifetime is very important. So if we can keep the cells working for longer, of course, it's much better for everyone. So now I guess Eitam get a lot of data to show us and to explain. So I'll let you present all of this. There are quite a lot of interesting data. Let's see that.
Okay, so with Carrar, we are performing a lot of tests together with OEM and self-research. In this specific test, you can see a drive cycle that we received from one of the OEMs. So let's start with the left graph. So we have the y-axis is the current, how much amps, and the time frame. Okay, so we have the same time frame. You can see that the current, the drive cycle is different, and it's running up to 2.5 C. On the right graph, we have 2 measurements. The green one is the cell temperature, and the purple one is the temperature of the vapor coming out from the module. And you can see that regardless to the C rate, okay, we have a very constant and steady temperature on the cells. Okay. So this is one factor. The second one you can see on the map below, on the top, sorry, you can see the number 3/10, 4, 6, 13. This is the different thermocouple positions on the cells, and the temperature uniformity that we received on the entire module. So between all of the cells, it was a 12 cells pouch module. We got a delta T of 1.25 degrees between everywhere, regardless again to the C rate. The second thing is the purple line that I mentioned, and this is how we measure the thermal resistance and therefore the efficiency of the system. If this line is very close, you have a very efficient system, and then you don't need to make a lot of to concentrate again on the different temperatures, on the temperature range between the module and the condenser, and etc. Okay, so this is a nice comparison that we have. The left one is a single-phase immersion. It's a test performed by XOS, and they have performed a charging and discharging protocol. The maximum C rate is 2.5 C. Flow rate was 12 liters per minute. The initial temperature was 35 degrees, and the maximum cell temperature was 45 degrees. The maximum delta T on the cells is 5 degrees. We can see a temperature increase on the graph, and you can see also the difference between the inlet and the outlet, which has, let's say, 2, 3, 4 degrees. And what you saw in our previous graph is that we have practically 0 temperature differences. So they have also high difference between the inlet and the maximum cell temperature, which also inflect the thermal resistance of the system. And this is a good solution when we'll compare it to a single-phase cold plate single phase. So, and now I'll jump to the right graph, to our graph. So all the yellow and brown lines are the different temperature measurements inside the module. Also here we had a different cells, but pouch cells, NMC, 12 cells. And we had an average C rate of 3, also for charging and discharging. It was continuous 3C. The flow rate was 0.3 liters per minute. The initial temperature is 25 degrees, and the maximum cell temperature was 27.2. So you can see that it's very, very, very steady temperature. The maximum delta T on the cells was 2.2. Also, it's very important to notice that the ambient temperature during the test was 32 degrees. Meaning that regardless to the ambient temperature, we managed to keep the cells at their comfort zone and optimal conditions at 25 degrees. So when comparing the two systems, you can understand what is the dimension of the pump comparing the two tests. And I will tell you that we tried very hard in this test to find a micro pump in order to have such a low flow rate. Okay, so on the battery lifetime, this is the gray line is a test that was performed by the Technical University in Munich, and they tested the pouch cells, LG pouch cells that are installed in the Audi e-tron, and they cool it down using a cold plate, and they charge and discharge the module at 2C charging, 2C discharging, from 20% state of charge to 80% state of charge, and going back and forth. So after 600 cycles, they reached the 80% capacity from the initial capacity, and this is already the end of life of the cells. And we decided in Carrar that we were lucky enough that the Technical University of Munich have performed this test, and we decided to repeat the test on the same cells. And after now we are passing the 2300 cycles, and we are at capacity of 90%. So this is a new information. So you can see here that we almost 4 times the lifetime than others than the cooling plate solutions.
At 2000 cycles,
300.
it's really a lot. So for automotive industry, it's enough. You can stop. So talking about safety and battery fire, this is of course one of the advantage when we talk about efficiency of thermal management. what about the ability to stop any battery fire? Do you have any data or anything you want to talk about that?
Yeah, so I can disclose a bit that we have performed a test on a thermal runaway, very aggressive test. And we managed to hold thermal propagation for 50 whole minutes on high energy cells. We are a very smart professor once told me, Professor from NREL, by the way, that if you will dissipate more heat than the cell is generating, you will prevent thermal runaway. So as you learned in the previous slide, Carrar capability to dissipate the amount of heat that being generated by a cell or by a group of cells, with our system, we can take care of this heat. So therefore, we won't reach the point that we have a runaway or a propagation. So the potential to prevent thermal runaway is enormous, and also thermal propagation.
So we have now some slides outside of batteries, but electric vehicles are not only battery technologies, they are also any kind of EV technology and power electronics. So let's see that.
Okay, so as you all know, like Cecile mentioned, we need to cool down everything inside the vehicle and not only the batteries. We are focusing, of course, on the batteries because they are the most critical factor and most expensive factor for the OEMs. But we see ourselves as a holistic solution, and we want to integrate all of our solution to address all of the different needs of the vehicle. So we developed also a solution for higher heat fluxes, higher power components. So in this case, we can see a solution that is suitable for inverter, converter, GPUs, CPUs, and etc. The test here was to try to cool down a heat source that is, the heat flux was 129 watt per square centimeter, which is a lot. And the goal was, or the success criteria was to keep the case temperature below 140 degrees when the ambient temperature is 55 degrees Celsius. You can see the green and blue line, which are the two temperature measurements. So you can see that they are very near, and the dotted purple line is the power, and the ambient temperature is the purple line below. You can see that when we reach the maximum power, we were around the 125 degrees at 55 degrees ambient, which is a huge success.
Just also to mention here that cooling of power electronic is very important for battery technology. You mentioned inverter, but it's also a huge problem, I'm going to say, for ADAS, for people trying to get huge amount of power computation, and also infotainment, because we have now in cars so much infotainment everywhere that cooling of power electronic is a lot of problem, I'm going to say. So that's a good option, of course.
Yeah, so this is another test that we have performed. By the way, I forgot to mention that we already broke our own record on how much heat flux we can take care of, and we reached the 280 watt per square centimeter, which is much higher than any components in the vehicle. So this one was developed for eVTOL use cases when they wanted to decrease the housing size, and they wanted to check if we can cool down two components, like different components on different sides of the evaporator. Okay, so we developed this very thin evaporator. It's about 13 millimeters thickness. And on one side we had like 5 components, and the other side were much powerful components. And the total heat dissipation was 2.4 kilowatts. We changed the ambient. This is why you see the jumps here. And we had two successful results. One is the temperature uniformity, which was around the 7 degrees. And the second one is that we managed to keep the case temperature below 85 degrees when the ambient temperature was 50 degrees. And I didn't mention here that the success criteria was below 95 degrees. So we were able to push it even further and still keep the components at their safe operational temperature range.
Okay, so we are nearly at the end of this presentation. While Tal is probably gathering a lot of questions, maybe a quick note about Carrar and who you are, where are you based, what is Carrar?
We almost forgot to tell who's Carrar is, huh? So Carrar is a startup. We are located in Israel. We design and develop, and we will provide the battery modules and thermal management system solution. So both the battery inverter converter solution and the overall thermodynamic loop. Our core technology, as you well understood, is based on two-phase cooling, two-phase, yeah. We're also making sure about heating up the cells if needed. So it's although it's a very innovative technology, but it's very mature. And as you know, it's very cost effective. As a small startup based in Israel, we partnered with more bigger companies so we can address the bigger market and accelerate our production or development. And we have Genterm as a partner and investor in Carrar, Roshling, also a partner, and Novelis. So with all the three companies, we are able to accelerate the go-to-market roadmap and product roadmap. And the
Sorry, go.
Yeah, and one last thing you can see here on the left, on the bottom left, a picture of our lab. So as a startup, we have a very impressive labs, and we can do testing on battery modules and packs. Even a small vehicle can go in the last walking chamber over there. And we have a small bunker that it's a secret what we are doing there, but we are planning to test thermal runaway, and soon we will present new results around how to prevent thermal runaway.
Yeah, I was lucky to visit you. Thanks for the invitation, by the way. If for those who want to see more, there are a couple of videos available on my LinkedIn where I made video visiting Carrar. So I guess we are ready for a Q&A session. I have seen that Tal has gathered several questions already. I think we have quite a lot. I don't know, Tal, you want to ask a question like that, or?
Sure. I divided the questions to first very technical ones. Then there's a bunch of questions, a lot of questions about the liquid, and then some general questions. Very interesting. So I'll start. Is immersion cooling suitable only for cylindrical cells or also for prismatic cells?
So immersion cooling solution is available for any kind of cells, whether if it's shape, so type, if cylindrical, prismatic, or pouch. We demonstrated on the three types, and it's also compatible with the different chemistries, so NMCs, LFPs, etc.
Okay. At what pressure was the data that you showed for the different boiling curves and boiling incipients? Could you give more detail on what parameters you changed in order to achieve a lower incipience boiling?
So this is the really core knowledge of Carrar. Thank you, Cecile. Yeah, I think two more back. No.
Okay.
Slide. No, it's the one with the curves or the boiling curve. So we tested it at low pressure. Yeah, the next one, this one. Yeah, so we tested it at low pressure, meaning that it's whether atmospheric pressure or slightly vacuum. It depends on the refrigerant. Our system is working or in a slight vacuum or in a slight positive pressure, but it's, I would say, approximately around the 1 bar absolute.
Okay. How do you handle the isolation risk in case there are metal particles that contaminate the fluid?
So we need to take care, of course, of how we insert the fluid, how we fill the system, and to make sure that there are no contamination of the refrigerant when we fill the system. And we have filters on the system to make sure that we don't have any particles going to places that we don't want them to go.
Okay, and this is a related question. How do you control the global ceiling?
So we designed the modules to be, of course, sealed. And for mass production solution, we are looking on laser welding or adhesives to seal down the modules. We are doing a lot of tests around permeability and material compatibility in order to make sure that we have the right materials, the right choice of materials over the lifetime, so we won't see any degradation in performance.
Okay, now we have some of what I call a slish and slosh questions that are about the liquid. Does the battery pack need to be fully immersed? If yes, how can reduction of coolant be realized versus conventional cooling? In my mind, you will need more versus cooling plate. Am I correct?
So we need, as we mentioned in the webinar, we submerge the cells, not the full pack, okay? And we are making sure the most of the volume inside the modules are actually the battery cells themselves. So in a module like this, in each module you will see here, when it's at about 12 cells, we have around the 400 milliliters in each module, and therefore less than 20 liters, around the 20 liters on the full pack, okay? In ethylene glycol solution, you also have around the same volume on a cold plate. On an immersion solution, we see numbers that can get up to 50 liters per pack. But because we don't need to circulate a lot of refrigerant, we don't need to have a lot of refrigerant in our reservoir, okay? So it's not a lot of refrigerant inside. You can see here in the movie, it's the nice boiling. I hope I answered the questions. If not, you can comment.
Just want to
Well,
mention
this
to
is a
people,
related question. They want to know how much liquid is expected to cool a full battery pack for a C segment EV.
For a C segment EV.
Yeah.
It really depends on the pack size. So if we're talking about 100 kilowatts or 40 kilowatts, so it ranges from 6 to about 20 liters, from 6 liters to 20 liters.
Okay.
just want to mention for those who have the opportunity to go on an exhibition or a show where Carrar get your module, you can see that's running. So if you go to battery show, for example, it was possible to see that. So you can better understand how immersed the things are. And there are also videos available on internet, of course.
Okay, the next question. What is the average additional weight of the system and the liquid?
So the average weight on a 100 kilowatt hour pack is we actually reduced the mass of the pack by 20 kilograms, as mentioned. And we did this analysis with 2 different OEMs. So we are saving weight. We are not adding any weight to the battery pack. On the module itself, we are reducing approximately between 100 to 200 grams.
Okay, a lot of people had confusion about what type of fluid are you using exactly? Is it oil? Is it refrigerant? And are you working with different suppliers?
So yeah, we're working with different suppliers. Carrar definitions of the refrigerant is that we need a right boiling point. So anything that ranges between the 18 to 35, 36 degrees will be good. Of course, it needs to be dielectric. And this is because we don't want to work in high pressure system. We can't use oils because the boiling point is very, very high. So, but we already tested and we demonstrated we can work with multiple types of refrigerants.
Okay, this is a question which is really general. I mean, it doesn't have anything to do with us, but I guess that person wants to know how much more expensive is the dielectric coolant versus a conventional coolant, which is water glycol. And do you expect this to change in the future?
Yeah, so it's a good question. It's the correct question. The refrigerant is more expensive than ethylene glycol, and I don't expect it to reach the price range of water. It's water are cheap. Maybe Coca-Cola is cheaper, but water is the cheapest coolant available. Also with ethylene glycol, of course. But yeah, I expect that the prices will be reduced by at least 40 to 50% when we'll go to mass production.
Okay. Someone is asking us if we're using hydrocarbons, fluorinated BAES, any esters?
So no esters, but we do use some fluorinated refrigerant as part of our testing. And as mentioned, we are testing we can use any refrigerant. We don't care about the specific chemistry, we care about the properties and that it boils in the right temperature, the electric, viscosity, of course, the density, but the technology itself, the beauty of it is that we can enable it and use it with any refrigerant.
How do electric isolation properties compare to dielectric oil? So I think that person wanted to ask maybe regarding how the dielectric liquid compares to dielectric oil.
So if I remember correctly, it's approximately 40 kilovolt, the dielectric resistance of this type of refrigerants. So it's high resistance. I don't remember the number for oil.
Okay, here's another cost question. What is the additional cost of the cooling system?
So when we compare ourselves, it's a hard comparison because you compare a system that can dissipate 6 kilowatt and doesn't extend the battery lifetime, and therefore you need to change. But if we were comparing a bomb to a bomb, so a bill of materials to a bill of materials, and that's it, with not taking into consideration the cost of ownership, assembly processes, and etc. We will be the range of 5% higher or cheaper, depends on the car itself, on the vehicle.
Okay, we have some more general questions. Even though more technical questions are coming in, I'm not sure we'll be able to answer all of them. Immersion cooling is currently mainly used in high-performance premium vehicles. Are you planning to apply the technology in mass-market vehicles? How long will it take before we start seeing this in these markets? Can we imagine this technology for all EVs?
You want to go?
I just want to mention that this is a plan. There are already many people trying to develop that for more mass market. How far is that going to happen? I don't know, but I can tell that from what I know, many people try to do that for higher volume for sure.
Yeah. So we are focused. Of course, first of all, the simple answer is yes. We do believe, of course, that we can implement our technology in all market segments. We do assume, and from the experience that we have, that the first implementation of the technology can be in heavy duties or hypercars or supercars. So Ferrari, Porsche, Lamborghini, Volvo Group, I forgot the name of the other company, Mercedes trucks and etc. can be a good candidate for penetrating the market. But I would say that the first companies that tested and still are in contact and testing with Carrar are the bigger OEMs, the passenger vehicle OEMs. So I think it's a good solution for everybody, especially around safety, performance. It's like the system that taking full advantage of the batteries. Yeah, so we can have high power batteries, high energy densities, and maybe minimize the pack size because we will be able to do fast charging.
Okay, there's some additional questions which I think it's important for us to answer because a few people asked them. In regards, are the liquids free of materials which are foreseen to be restricted in the future? I think they're talking about PFAS. And yeah, there's another question. Are fluorinated liquids not going to be banned in the EU in the next couple of years?
Yeah, so we are very aware of PFAS regulation and the trifluoroacetal refrigerant. Yes, they are going to, some of them going to be banned, but some of them are not going to be banned. And we making sure to use the one that are in the high probability not to be banned. There was in the past the TFA regulation, which most of the refrigerant were subjected to this regulation. And now the PFAS regulation is, of course, a wider, more strict regulation, but we don't think, or almost sure, that the refrigerant that we are using won't be subjected to the PFAS regulation. And we know that it's everywhere, yeah? So we have PFAS in our clothes, in the batteries, in everything. So, it's a good question, but we are taking good look into it and making sure to use a refrigerant that won't be subjected to PFAS regulation.
Okay, someone asked about the pressure in the module battery. You answered that already. There's one last question that I want you to answer. Do we have time before that to a couple of more questions?
We have time.
Okay. Have you tested the system under acceleration?
So we are testing the system under the different standards, UN 30.3 on different SAE, ISO, and etc. So yeah, the system is, because there are like blocks of the volume inside the module, it's not most of it liquid. We are not worried about acceleration or angles or etc. We solved all of these issues to making sure that we don't have liquid splashes inside the module. So we are designing for it, of course.
You can see some details of this on one of the video I made at battery show, for example, with the float.
Okay,
right.
Here's a related, sorry, should I continue? Here's a related question. How do you achieve vibration and shock test using liquid cooling technology? And how do you perform in vibration and shock, during vibration and shock?
So making sure that during the test, the module is perfectly sealed. So we are blocking the inlet and outlet of the module, and doing like anybody else, any other technology is doing. So we are taking the module and we put it on a shaker.
Okay, is immersion cooling, as we propose, compatible with CTP architecture?
CGP.
What? I'm not familiar with this.
I also don't understand.
Okay.
This person can contact either Eitam or myself with maybe more detail and maybe
Sure.
understand.
I mean, I can give your email addresses afterwards. If your refrigerant liquid could be used in the AC loop, if yes, do you make some validation?
So we make validation on integrating with the HVAC loop, but because the refrigerant in the AC loop is boiling at minus 18 degrees and they are working in higher pressures, I don't think it's efficient to switch it, but we do, with one of the refrigerant, we do looking into it, but the most of the work that we are doing is to integrate with it, and we want to help the HVAC system. We want to deliver the heat in order to heat up the cabin.
Okay, please comment on safety aspects. Namely, please walk me through an example of a refrigerant leak. I think we talked about this previously, but that's another question.
Yeah, so when we'll have a refrigerant leak, will be sensitive just as a single phase solution, right? So cold plate solution. But as long as we don't have a leak and we are making sure that we will pass all of the vibration, crash, and etc., and don't have a leak or thermal runaway events and etc. So the module is designed to hold thermal runaway event, and we still will design the pack in order to, so if we will have a leak and thermal runaway will happen, so we'll have the same safety measurement like in today's systems.
I think we can get one last question because we are near the end. So one
Sure.
last question.
Okay. There was one question, what about trucks and buses? I can answer that. We do buses and trucks. We do all types of batteries for all types of vehicles. The last question is, what is the biggest challenge to implementing immersion cooling in a vehicle?
Psychology. We need to convince a very old technology. We need to make now they are very familiar with the ethylene glycol technology. It's very commonly used in ICE engines, and this is the first thing they tested, but they also tested two-phase. So we need to always to penetrate and to present a new technology is a challenge, and this is, I think, the major challenge of Carrar. And now when immersion solution will become wider spread or wider expected in the market, also two-phase cooling solution will be accepted and adopted by the major players.
Okay, I think we are on time. Shall we close up? I know there are maybe other questions. I have personally other questions, but I can ask you later, Eitam. So thanks everyone for joining. You still can contact either Eitam or myself if you are in this webinar. I guess you know how to find us, at least on LinkedIn. Don't hesitate to ask any question and we can come back to you. Also for those who are interested to test with Carrar, of course, don't hesitate to contact Eitam. So thanks everyone. Enjoy your day wherever you are. And thanks Tal also for the great technical support. Thank you.
Thank you.
Bye everyone. Bye.
Bye-bye.